Hello everyone, this is Omer Anwaar from Asameto Global R&D team, and the topic of my presentation today is nonlinear analysis of circular composite columns, the design methods according to Eurocode 4 Part 1. So I have structured my presentation starting from the introduction to composite columns, design methods according to Eurocode 4 Part 1. These will include the design methodologies to generate NM interaction curves, comparison of these interaction curves, and the parametric study. To carry out the parametric study, a small tool, an Excel tool, was created in this research project, which was used to compare the different interaction curves. And finally, I will present the conclusion. So a very brief introduction to composite column here. A composite column, and in this case a steel concrete composite column, uses a very high compressive strength of concrete with a high compressive and tensile strength of steel. This results in ductile and very stiff sections, and also resulting in slender columns. And in fact, this also saves space in a building. The steel tube outside this composite columns also provides confinement to the concrete. This results in a higher compressive strength of the concrete or of the overall section. Also, the concrete encasing the steel profile inside the cross section also provides fire protection and increases its buckling capacity. Overall, a composite column results in an economical design, and it contributes to faster construction. So we'll look at some design methodologies in Eurocode 4 and how to design a composite columns and which approaches are available. So in Eurocode 4, different verification methods are possible, and depending on the type of loading, and in this case on your left under concentric loading, a simplified method can be followed. If there is only axial force applied, we can go ahead with designing the column according to European buckling curves, or we can make a simplified NM curve using linear polygons, just joining 4 points, which you will see further, and apply the theory second order. Or we could also follow another route where the resistance of the member is calculated for combined compression and bending. This also uses the NM interaction curve, so polygon based, and using the theory second order. On the contrast, if we have eccentric loading, we can still follow the NM curve with theory second order, but we can also approach the problem using general method where any cross-section can be used and any combination of material can be used. So let's look in detail the simplified method using European buckling curve and some general limitations. And in this case, the concrete strength is limited until C50, and the steel grade which can be used is S460, whereas the reinforcement of 6%, the maximum reinforcement of 6% can be used. If we look at the simplified method limitations, only doubly symmetric cross sections can be designed. The uniform and the cross section, in fact, the column cross section should be uniform over the length. The steel contribution ratio should vary between 0.2 and 0.9, and the relative slenderness should be less than 2. Also need to be respected the B by T limitations for each cross section, and once we have these limitations checked, we can calculate the reduction factor using the European buckling curve, and eventually the resistance of the cross section. So if we have combined compression and bending in a simplified method, we can generate a linear NM interaction curve. And this curve can be generated first by identifying these 4 points. So A, B, C, and D. A point represents the maximum normal resistance of the cross section. And in this case, the cross section the point A is completely under compression, so the concrete and the steel both are under compression. Coming next to point D, this is the point which represents the maximum bending capacity of the cross section. So here in this case, a normal the neutral axis is moved on the cross section. In this case, in the middle of the cross section, and this using this, we can calculate the maximum bending resistance of the cross section. So coming to point C, this is the point for a normal force corresponding to which we have the plastic, the bending resistance MPL-RD. And the point is, point B on this interaction curve is where the cross-section has no a normal capacity, so the normal force capacity, but only the bending resistance. So next I would discuss different NM interaction curves which are possible. So far we saw the simplified approach and the linear NM interaction curve. We'll look at how the exact plastic interaction curve can be made and the strain limited curve can be made. So for an exact plastic interaction curve, this uses rectangular stress blocks without using the strain limitations of any material. In this case, you see in the bottom a circular CFST column, and you see in the red dotted line the neutral axis, so plastic neutral axis, and in basically a cross section is divided into many small fibers, and each fiber for each fiber a normal force and is calculated, and the moment is calculated based on the stresses for each material type, so concrete reinforcement, and if there is a steel tube outside or a steel profile inside. And as we move this neutral axis across the cross section, we can generate the different stresses which are formed or generated on the cross section at that particular neutral axis. And in the bottom figure, you see the whole cross section is under compression. So you have the maximum compressive strength of concrete, steel reinforcement, and so on. And if we can calculate the normal force and the bending moment in each fiber, they can then be represented in a loci of points to form an interaction curve, and this we would call an exact plastic non-NM interaction curve. If we look at the strain limited design methodologies, we saw earlier the plastic design based on rectangular stress blocks with no strain limitation. Of course, this is not the method which we used as it is, but the more exact way of generating NM interaction curve would be using the strain limitations, and in this case of the concrete and steel. As mentioned earlier, the strain limited design methodology involves the strain of the material, and in this case for concrete I used a parabola rectangular diagram for concrete under compression, and you can see different formulation for using which we can calculate the stresses based on the strains in the cross section, followed by the bilinear model for reinforcing steel and for structural steel. Also to mention that the maximum strain taken for structural steel is 20 times epsilon yd. So for strain limited design methodology, different steps which were used to generate these curves started with the discretization of the cross section into small fibers, and then the distribution of the strains, calculating the strains or the stresses based on the strains and for each material, and finally calculating the N and for the normal force and the moment resistance of the cross section for each fiber, and eventually using all these points to generate an interaction curve. You're looking at the strains and stresses on a composite section. This starts with the distribution of the strains and calculating the curvature. This can be calculated using the small formulation based on the strains in steel and of concrete and the distance between them. And based on this, we can calculate the stresses in concrete and stresses in reinforcement and steel tube and the steel profile. So a brief overview on how the strains are distributed on a composite section. I've divided this into three zones, so any cross section into three zones. Zone 1 represents a rotation about point A, so capturing all the combinations of strain in a composite section. A rotation about A is carried out where epsilon S1 is fixed at epsilon UD, so this point of strain of the steel, and the strains are varied from the concrete maximum concrete strain epsilon CU2 to epsilon UD. In a similar fashion, rotation is carried about point B, where this maximum concrete strain is fixed. So for example, arbitrary value of 3.5 per mil, and the strains in steel are varied from epsilon UD to point between 0 and epsilon C2. And lastly, the rotation is carried out about point C, where the strains in are moved between epsilon Cu2 and C2, and the steel strains are varied between minus epsilon C2 and minus epsilon Cu2 by H. And once we have captured all the strains and the methodology described earlier, we can calculate the curvature at different locations, and followed by calculation of stresses and eventually the N and M values for different fibers, generating an NM interaction curve based on strain limits. So finally, the comparison of NM interaction curve here. So once all these different methodologies were implemented in a small tool, so namely the simplified curve, the exact plastic NM curve, and a strain limited curve, they can now be seen all together, and you see that the exact plastic curve lies outside the strain limited curve. And for this reason, we use an alpha M value. And alpha M value is a reduction factor which is applied on the bending resistance, so the bending values of a cross section. This pushes the curve backward and inside the confines of a strain limited curve. But you would notice that the exact NM curve still lies outside these confines of strain limited, and that's why we don't use exact NM curve, but rather we use a simplified NM curve, which is generated using different points on this exact curve, so A, B, and C, D points. To further investigate this alpha M reduction factor, I have named them alpha M1 and alpha M2, which represents the ratio of strain moment due to the strain limited design and the moment due to simplified plastic design. And in the similar fashion, alpha M2 strain limited by plastic exact. These alpha M values are then represented on a curve showing the limitation set by Eurocode. And as you saw in the previous slides, Eurocode defines a value of 0.9 when using a steel grade of up to 355 and 0.8 when using a steel grade of 460. And you can see that the alpha M1, which is strain limited by simplified curve, it lies for an arbitrary section, it lies below the limitation set by Eurocode of 0.9, whereas strain limited by plastic is exceeding this value for a different location in the cross section. And to investigate this phenomena further, and especially to see the effect of using the steel tube in a composite cross-section, a parametric study was carried out. And in this here you see a cross-section of 245 millimeters and satisfying all the conditions of a simplified method. You see that the alpha m values for strain limited by simplified method are within the limit of 0.9, but the moment this curve, a cross section without a steel tube is used and still following the limitation set by outlined in simplified method, we have the alpha m value which exceeds, and that's where it becomes unsafe. So to further enhance on this idea, a parametric study was carried out in detail, so we could capture this phenomena for different cross sections, namely the cross section diameters, steel tube thickness, steel using different steel profiles, different concrete and steel grades, and reinforcement ratios. This input parameter was also further subdivided into different categories of cross section. So for example, category 1, you see outside steel tube with normal concrete and steel grade, and category 2 you see with no steel tube and normal concrete and steel grades, and so on. And what we noticed that for category 1, which is with the steel tube and normal materials, strength of materials, it satisfied the criteria set by Eurocode of 0.9. But the moment steel tube was removed for category 2 cross section, the curves become unsafe. So the alpha m value was not respected anymore. When it was checked for steel tube and without steel tube outside, but using high strength concrete, none of the curves they respected the alpha m values, which is fine because Eurocode 4 is limited until C50 as of this moment. When the curves were checked for normal strength concrete, but using high strength steel cross section, some of the curves they exceeded this limitation of 0.8 in this case, and this needs to be looked at for higher grades of steel. Finally, some takeaways from this presentation. The concrete strength, when it is lower than C50, the alpha M values or the reduction factor given by Eurocode 4 part 1 can be applied for simplified linear NM interaction curve in most of the cases. But when the composite cross-section without the steel tube was analyzed, the alpha M reduction factor suggested by Eurocode 4 was not always on the safe side. And also, this work points out that Eurocode 4 should clearly exclude the encased round section without steel tube outside, and mention that this is only applicable for rectangular cross sections. And finally, for concrete grades beyond C50, the alpha M reduction was not sufficient for composite columns, even with the confinement effect of steel tube, so alpha CC value taken as 1. The plastic design has to be reviewed for the application of high strength material. And thank you for your attention, and if there are any questions.